Hey team, welcome to our first online lesson here. So we're working on 2.5 rational functions, and I just want to warn you that this is going to be a very basic overview of just one type of rational function. There are really an unlimited amount of types of rational functions, and the graphs can get really kind of crazy and cool looking. So please, I encourage you to pop in to office hours this week just to get some more exposure to the different types of rational functions. I will show you a few examples at the end just as kind of some visualizations of what rational functions can look like in kind of the crazier forms. But just know we are kind of keeping this to bare bones just because of the fact that we have moved online for this semester. What I want you guys to do is make sure you print out the PDF notes that are going to be associated with today. So look up Monday, March 30th, and there should be a PDF copy of the notes that we're going to be working on today, so that way you can follow along with me. So for our warm-up, I want you guys to work with a generic function. We're just going to keep it f of x. I'm not going to define it as anything other than f of x. And I want you to write a new equation that follows these following transformations. So go ahead, try that, pause the video, and then we'll come back and we'll see how you did. All right, hopefully you had a chance to go ahead and try these transformations. So f of x is going to get shifted to the right 5 units, and that's going to become our new function h of x. So if you are doing a horizontal transformation, it is going to go inside with the x value, and it is opposite of what you think. So if it's going to the right 5 units, that's going to be an x minus 5. So h of x would equal f of x minus 5. If we are going to shift f of x down 7 units, that is going to go outside of the function because that's what vertical transformations do. So this is going to be f of x minus 7. K of x is going to shift f of x to the left 2 units, so that's going to be an x plus 2, and then up 4 units, so that's going to be plus 4. And then L of x is going to reflect it over the x-axis, so that's going to have a negative out front. That's how we're going to get that reflection. Let's start by graphing the most basic rational function that we can. We actually did this the very first day of class, and we said we would talk way more in depth about it later on this semester, and here we are. So let's start with the table of values. I'm just going to give you kind of a bunch of points I want you to work with. So I'm going to give you all of those negative values. I'm going to give you 0, and then I'm going to give you all the exact same numbers, but positive. So here we go. Plugging in negative 5, that would give me 1 over negative 5, so that's a negative 1/5. Plugging in negative 1 would give me 1 over negative 1, so negative 1. Plugging in a negative half looks a little bit funky, so this is 1 over negative 1/2. I'm actually going to kind of work off to the side here so I can show you what's happening. This is what's called a complex fraction, and it just looks ugly because it's a fraction within a fraction. So if I just do one step just by rewriting it with different notation, I think that already makes it look significantly better. And just remember, when we divide fractions, you're really multiplying by the reciprocal. So this is really 1 times a negative 2 over 1, so that's really 1 times negative 2, so that just gives me negative 2. So that same idea is going to happen with negative 1/10 when we plug it in. We're going to get negative 10, and we'd get negative 100 when we plug in negative 100th. Now, when I plug in 0, that gives me 1 over 0. And this function, or that value, is actually undefined because 0 is not a part of the domain. 0 would actually make the denominator 0 there, and we can't have that. Let's plug in the rest of the values, and we end up with some numbers like that. So do the best you can to get these sketched. That's as much as I can fit on this left-hand side here because I don't have enough room on my vertical axis to go all the way down to negative 100. Just know that when I plug that value in, it's going to be somewhere way down here, and it's getting really close to the x equals 0 value, but not quite. Let's skip over. So I'm not going to have any y value when x is 0, and then I'm going to work off on the other side. So 1/10, comma 10, 1/2, comma 2, 1, 1, and 5 1/5. Now this graph is kind of unusual because it's actually going to be in 2 pieces. Ooh, that wasn't a very smooth drawing for me. And we're going to do this side. So this rational function actually looks something like this. Let's answer the essential questions about it. So let's take a look at domain and range. So for the domain here, notice everything worked but x equals 0. And you can also kind of visually see this. I get really, really, really close to 0, but I'm not actually touching 0. So for my domain, it's going to be everything but 0 because I don't have x equal to 0. And for my range, I'm actually going to have the same thing. Notice my y values get really, really close to 0 here. I'm using the highlighter here just to indicate that I'm getting really close to these values, but I'm never actually touching. So my domain and range are actually going to be the same thing for this. The domain means my x values are everything but 0, and my range means my y values are everything but 0. As far as intercepts go, just a visual check on this graph, I don't see where it's crossing the x-axis or the y-axis, but you can also verify this just by plugging in and algebraically solving for this. So x-intercepts is when the y value is equal to 0. So if I'm solving this equation, 0 equals 1 over x, notice if I multiply both sides by x to get that x out of the denominator, look at what's going to happen to the x and what kind of statement we're going to be left with. X times 0 is 0, 1 over x times x is just 1, and 0 most definitely doesn't equal 1. So that means there are no x-intercepts. So let's look for y-intercepts. That's when the x value is going to be equal to 0. So I get y equals 1 over 0. Well, we know that can't happen because we can't divide by 0, so that tells me there's also no y-intercept. Symmetry, we do have symmetry with this graph. So this graph is symmetric about the origin. So if you look here, if I pick a point over in this quadrant, I can map that through the origin, and notice I have a point on the other side of the origin that it maps to. So when I plug in the point 1, 1, I get the point -1, -1 out. When I plug in the point 1/2, 2, I get out through the origin here. Notice my mapping. I get out the point -1/2, -2. Or the point 5, 1/5. I can map this through the origin, and I get out the point -5, -1/5. So we do have symmetry. So you can say that this is going to be an odd function, or you can say there's symmetry with respect to the origin. But I would suggest just saying odd because that's shorter and sweeter. Let's keep going with the essential questions here. So as far as the end behavior goes, these first two questions should look very familiar. So as x approaches -infinity, what is my y value doing? So as x goes out here to -infinity, what is my y value doing? Well, my y value is getting really, really, really close to 0. So we'll go ahead and say, as x approaches -infinity, f of x is approaching 0. And then let's look as x approaches +infinity. Well, f of x is also approaching 0. So those two are the same. We've seen those before. The only difference being here that f of x is actually approaching a specific number versus approaching positive infinity or negative infinity. These next two are a little bit different, so I have some new notation here. So this third one down, as x approaches 0, and we have this little superscript with a negative sign right here, that means 0 from the left. So as I come over here and I'm looking at my graph, as x approaches 0 from the left, so as my x value gets really, really, really close to 0, what is y doing? Well, look at what my y value is doing down here. As my x gets really close to 0, y is going off to -infinity. And I can kind of see that happening right here with this point. When I plug in -1/100th, my y value is going down to -100. So if I plugged in -1/1,000,000th, then my y value would be going to -1,000,000. So my y value keeps getting bigger and bigger and bigger in the negative direction. So I'm going to say that's going to -infinity. And then for the fourth one, as x approaches 0 from the right, that's what that little superscript with the plus sign means. What is my f of x doing? What is y doing? So as we are looking at my x values now from the right-hand side, well, my y values are now shooting off to positive infinity. Intervals of increase, decrease, or constant. Let's go back and look at the picture here. So let's look at this first left-hand side. Sorry, I have a whole bunch of markup on this graph. Let's, I guess, pick a new color. So as I'm walking on this side, if I'm a little bug walking on this piece of the graph, notice I'm walking downhill. So I have an interval of decrease there. And then as I move to the second portion, I am still walking downhill. My y values are getting smaller. So this one has 2 intervals of decrease. So intervals of decrease here, we would say from negative infinity to 0, union from 0 to infinity. As far as increase and constant go, there are none for this particular function. All right, I kind of want to go back to the idea of the warm-up. So working with that rational function, f of x equals 1 over x, I want you to write a new function that's going to shift it 5 units to the right. So this is going to be called h of x. And if f of x is defined now as 1 over x, if I'm going to shift that to the right 5 units, that's going to give me an x minus 5 in the denominator. Because again, it's going to go with the x value, and it's going to be opposite of what I think. So if I look at a quick sketch right here, I'm going to shift it to the right 5 units. So I'm going to draw a little kind of a vertical line right here. I'm going to dash it. It's not really part of my graph, but I'm going to use it as a guide to help me visualize this graph moving to the right 5 units. So nothing else has changed other than this graph has moved right 5 units. So it's going to be doing something like this. I do want to take note. Notice I still don't have any y values that are equal to 0 here. So I'm going to kind of dash that line right there on the x-axis just to be like, hey, I'm getting really close to that x equals 0 value, but I'm not actually ever reaching it. Sorry, y equals value, but I'm never actually reaching it. We'll just look at a few things here. Let's look at domain and range. The domain of this graph, so if I go back and I look at this denominator, what makes 0 here? Well, 5 makes 0, so that's my problem value. So negative infinity to 5, union 5 to infinity is what's going to work. For my range, since my graph didn't shift up or down any, my range hasn't changed from that parent function. So negative infinity to 0, union 0 to infinity. I don't have symmetry with this particular graph because I moved it to the right 5 units. I lost that symmetry with respect to the origin. All right, let's look at the next one. Let's look at b. So we're going to look at function j of x now, and we're going to shift this down 7 units. So if f of x is defined as 1 over x, if I'm going to shift a graph down, I'm going to have it outside of what's with the x value, and it's going to be exactly as is. So if it's going down, that's going to mean it's going to be a minus 7. And let's look at a visualization here of the graph. So down 7 units is going to put me down here at negative 7. And I'm going to draw a little dash line right here. I'm going to put another dash line going down the y-axis because I'm still not going to be able to have an x value of 0 because notice that would still cause problems in my denominator. So now I can kind of go in and just sketch my graph. If you want some more specific points on here, you're welcome to go ahead and make a table of values. But here's just a rough sketch of what that picture is going to look like. Domain and range here. Domain is going to be everything but 0. So we're just going to skip over 0. And range now is going to be everything but that negative 7. Now, one thing to keep in mind is this j of x function could look like this, but j of x could also be cleaned up. So think about if we actually did the subtraction here with the 2 fractions, and what that's going to look like. So what would happen here is I would need to get a common denominator. So both top and bottom, the numerator and denominator of 7 over 1 is going to get multiplied by x over x. That really means I'm just multiplying by 1. Uh-oh, I'm sorry, I just deleted some stuff here. My hand hit. There we go. Okay. So we're going to have 1 over x minus 7x over just x. Now that I have a common denominator, we can go ahead and just do the subtraction. So 1 minus 7x all over x is another way that j of x could be presented. They're the exact same graph. The function, just the way the functions are written, happen to look a little bit different. All right, let's look at k of x. And we're going to be shifting it left 2 units. So that's going to go with the x and opposite of what we think. So that's going to be 1 over x plus 2. And then up 4 units is going to be plus 4. Since we just did the last one, let's go ahead and actually rewrite this one before we do any kind of graphing of this. So I need to get a common denominator. If this is my denominator, then that tells me both top and bottom of the 4, because think about that, that could have just been 4 over 1, are going to get multiplied by x plus 2. If I do the exact same thing to the top and bottom, it's as if I'm really multiplying by 1, which is totally legal to do. So I have 1 over x plus 2 times 4x plus, it looks like 8, if I distribute that 4, all over x plus 2. So I can combine like terms. 4x plus looks like 9 all over x plus 2 is another way that my function could be written. That and that both represent the exact same function. So let's graph it. I think it's a little bit easier looking at this initial equation to think about what's really happening with the graph here. So left 2 units, I can kind of easily visualize that, and I could definitely sketch in this vertical line right here at -2, and I could sketch it in going up 4 units. Again, I'll do another little dashed line right here, and then I can just plot my graph. I can draw my lines and just do as good of a sketch as I can do here. It's not going to be perfect, but it'll be pretty close. So I can see what it's going to look like here. Notice with the rewritten equation here, x plus 2, that -2 still causes a problem in the denominator, meaning we're going to be dividing by 0. And then notice we have this right here with that vertical line. So let's look at domain and range. So my domain would be everything but that -2, because that's what makes 0 in the denominator. And my range is going to be everything but +4. So think about it, that graph got shifted up 4 units, so 4 is now the problem. All right, last one here, D, L of x. This is going to be f of x reflected over the x-axis. So the equation itself isn't very exciting. It's just going to have the negative sign out front. And then let's go ahead and reflect this. I'm not shifting it up or down any. I'm not shifting it left or right any. So I'm just going to have those 2 dashed vertical lines right there on the axes. And if I'm reflecting it over the x-axis, think about it, this piece that was up here in that first quadrant is now going to be down here in the 4th quadrant. And what was down here in the 3rd quadrant is now going to be up here in the 2nd quadrant. So it's going to look something like that. Domain and range don't change from the original parent. I still can't have 0 for either x for the domain or y for the range. All right, this whole time we've been leading up to the idea of these crazy things called asymptotes. So what an asymptote is it means you get really, really, really close to a value, but you never actually reach that number. So rational functions have technically 3 types of asymptotes. You can have a vertical asymptote. You can have a horizontal asymptote. Or you can have a slant, or sometimes it's referred to as an oblique asymptote. These are the 3 types of asymptotes that you're going to see with rational functions. For our purposes, we're going to be spending most of our time with vertical and horizontal, but I'll talk a little bit with my other examples here about the slant or the oblique asymptote. So I want to go back and look at our parent function. So I apologize, this is super messy, but let's see what's going on here. So as we're getting closer and closer and closer to 0, let's find a color I haven't used here. I don't have too many options. As I'm getting closer and closer to 0, so let's say, let's look at this -1/100th. Okay, that's getting pretty darn close to 0. Look at what's happening here. I'm getting this y value that was way down here. It's way down here at -100. If I went to -1,000th, that means my y value would be a -1,000. So my y values keep getting bigger and bigger and bigger, and it's kind of yielding this vertical asymptote right here at x equals 0, meaning I'm getting closer and closer and closer to x equal to 0, but not quite. And my values, my graph here is either getting really close on this side, or if we look at the upper portion of the graph, it's getting really, really close on the other side. So a vertical asymptote what that's going to look like is it's going to be an x equals line. Okay, you're actually going to write the equation of the vertical asymptote, and it's going to be whatever makes the denominator 0. Okay, so let's go in for all of our examples and write in what the vertical asymptote is going to be. So my vertical asymptote for this one would be the line x equals 0, because 0 is what makes the denominator of 1 over x 0. Let's look at this one now. What makes the denominator 0 here? Well, that's going to be positive 5. So my vertical asymptote would be x equals positive 5. So again, it's a vertical line because it's a vertical asymptote, and I'm getting closer and closer and closer to this line, but I'm never actually touching it. For my next example, my vertical asymptote here is still at x equals 0. It didn't shift left or right any, so my vertical asymptote would be the equation x equals 0. Again, looking at here, like with the denominator, you can see that's what makes 0. Or back up here, the only thing that's in the denominator here is the x. So again, 0 is what would make the denominator 0. If we look at c, what's going to make the denominator 0? Well, if I look at it here or I look at it here, my vertical asymptote is going to be at the line x equals negative 2, because that's what makes my denominator 0. And my last one, my vertical asymptote is going to stay at x equals 0 because I haven't shifted it left or right any. For the horizontal asymptote, there's actually a couple of different scenarios here, but again, we're keeping this pretty basic. So for a horizontal asymptote, we are going to be looking at same degree functions, where the degree of the numerator, I guess we're going to be looking at two scenarios. We're either going to have, okay, this is silly, same coefficients are lame scenario, or we're going to have bigger below y equals 0. I taught in Texas for a few years, and this was a little mnemonic device that I picked up there, or a little memory trick to help me remember how to do each of them. So we're going to have one of these two scenarios that we're going to be working with for our rational functions. So let's talk about bigger below y equals 0. So going back to our original parent function here that we have for my horizontal asymptote, we're talking about the degree. So the degree of the denominator for this one is 1, because that's really x to the first power. And of our numerator right here, this would be degree 0, because there is no variable, there is no x value there. So a constant is just a degree 0. So you have a bigger degree below. That means you're automatically going to have a y equals 0 horizontal asymptote. You can kind of think about it as you plug in values for x. I think about plugging in a really big number. If I take 1 divided by 1,000,000, that's essentially 0. Or 1 divided by 1,000,000,000,000, that's essentially 0. Not actually 0, but really darn close. So you're automatically going to a y equals 0 scenario. So I can have that type of instance. So if we look at this one that we have, our part A, I have bigger below because I have degree 1 on bottom and a degree 0 on top. So this guy has a horizontal asymptote at the line y equals 0. Bigger below, y equals 0. For this one now, notice I have the exact same degree on top and bottom. I have a degree 1 over a degree 1 because this has to the first power over something to the first power. And we can see that we have a horizontal asymptote at the line y equals -7. So when that's the case, let me get a new color and try to get this mildly organized here. I'm going to rewrite j of x just off to the side here. And I'm going to put that 7x first, that -7x first. What happens here when you have the same degree, so this would be the same coefficients are lame. It's terrible, but it kind of helps you remember it a little bit. So same coefficients are lame. We have the exact same degree. I'm going to put a little 1 in front of the x just so we can see what's happening here. This means I'm going to have a horizontal asymptote at the ratio of the coefficients, of the lead coefficients. So -7 over 1 would clean up to give me -7. With this one, ooh, this is a great one to look at. So it looks kind of funky here. So this would be another instance of same coefficients are lame. So here, I might put a little 1 in front of the x. I'm going to look at the ratio of the lead coefficient. So I have 4 over 1. So this tells me I'm going to have a horizontal asymptote at y equals 4. And look at your graph. You can see I don't have any y values at positive 4, and I can quickly get that from that ratio. And then let's look at our last one here. This would be a horizontal asymptote. I can look at my rough sketch right here, and I can see that I have y equals 0, or I can see that I have big or below. So that means I'm going to have an automatic y equals 0 for my horizontal asymptote. A slant or oblique asymptote is going to occur when you have a larger degree in the numerator. So the mnemonic device for this one is bigger on top, stop, and do long division, because that would help you figure out what that oblique asymptote is going to be. All right, I want to show you just a few kind of funky examples here. So this first one right here is pretty similar to what we've been working with. One vertical, one horizontal asymptote, and we have the two pieces. So that's kind of like an example that we've seen and would totally be fair game for an exam question or a quiz question. This second one, you look at it and you're probably like, wait a minute, that looks like a linear function. Well, it's really, really close, but this little open circle right here is actually what's called a hole in the graph. And we won't have time to talk about holes, but I encourage you, if you're interested in this or you know you're going on to the calc series, talk to me during office hours about it, and I can give you some examples of when you would have a hole in the graph, because something like that definitely could happen. You can have instances with rational functions where you actually cross the horizontal asymptote. So look at this middle piece right here. We have a horizontal asymptote at y equals 0. Yet I'm crossing that asymptote. So sometimes that can happen. Like I said, there's a lot of really funky behavior that can happen with rational functions. You will never, ever, ever cross a vertical asymptote, but sometimes your graph could cross a horizontal asymptote. It just depends on the behavior of the function. The reason you can't cross a vertical asymptote is because that would mean that you're dividing by 0, and that's not possible. This next one is just another kind of funky looking one. Just to show you that sometimes your pieces of your graph might be going in the same direction. So both of those pieces, as x approaches 0, are going off to positive infinity. And then this one right here would be an example of having a slant or an oblique asymptote. You can see the vertical asymptote here at x equals -2, but this one is not horizontal. It's actually a slant asymptote, so it's following some kind of line. Looks like this one would be following, if I can quickly do this, looks like x minus 2 for that line. Has a y-intercept here of -2, and it looks like we're going up 1 over 1 for our slope. So sometimes instead of following just a straight up y equals line, it follows a line that has a slope to it. So again, just to give you some ideas of what rational functions can look like, because they really do get crazy. Homework for tonight will be Connect Math. It's not ideal, but it is what it is. And good luck. Let me know if you have any questions, and pop into office hours this week and ask them. Thank you so much. Bye.